Now let us discuss like combinational circuit design. So this process is basically has several steps in it. It starts with writing a specification. So as any engineering project, when you go to a customer and meet with them, discuss their need, outcome of that meeting is usually a specification of the software process for you guys, or any engineering, like any engineering project as such. Outcome is a specification of the need, right? So that has to be agreed upon with your customer and yourself, so that everyone is clear on what is required to be done. Now from that, in a digital logic design domain, from a specification we need to formulate a function through a truth table. Okay, through a truth table. Then optimize the boolean function into the reduced form. So we all know, like, once we have captured the whole solution of the given problem in a truth table, then we can use a K-map technique and other things to have a reduced boolean function for that specific problem, specific solution of that given problem, and then map this function into the available logic gates. So just to note, like, not all the time all the logic gate is available for several reasons. So you should not assume that whatever reduced form you come up with that can be implemented on to your target product, because some of the logic library so maybe missing. Okay, you probably don't have those components in your hand, so you need to work with whatever available to you. So there actually goes some logic transformation, but your logic function needs to be the same, whatever your transformation you do on top of your reduced boolean function. Okay, and very last but definitely not the least step is to verify your logic circuit. So in this class we'll go through and sample example, and like, let's say we start from a specification. We look at the problem statement and try to build a truth table for that problem statement, and then we use the K-map technique to come up with some reduced formula, and then we map the function into available logic gates. Verification of the logic is more like a manual in this class, or at least for this example, but we will do like, there are more automated way of doing verification, and verification is a big industry itself. Like, it basically tests if your product is working as per the requirement. Okay, as per the requirement. So verification testing is very big industry, uh, irrespective of type of product. It's important in digital circuit design, it important in analog, it important in any other engineering product. As such, any product, there is a test team and QA team, quality assurance team, which basically verify that your product conforms to the requirement. Okay, so let's start with the specification. So the problem or the specification says that, okay, the XS3 code for a decimal digit is a binary combination of the corresponding decimal digit plus 3. So we are dealing with the decimal digit, not the decimal values or number, just specifically a decimal digit. For a decimal digit, as an example, let's say 5, which has a 4-bit binary of 0, 1, 0, 1, and the XS3 code for 5 would become like 5 plus 3 equals 8, right? And then which is 1, 0, 0, 0 in 4-bit binary. So that's an example. So we through this digital circuit, what we are trying to do is that take a decimal digit and transform into its corresponding XS3 code. Now we need to implement a logic circuit which will translate this a 4-bit BCD binary coded decimal, where each decimal digit is converted into corresponding binary digit into its XS3 code. So with all these things, what essentially this means, if I'm assuming you know what is a binary coded decimal is, so if you don't know, a binary coded decimal is basically, let's say I'm talking about a value 425, a decimal value. We all know how to convert it into a binary, right? Like whatever binary number, let's say 8-bit binary and stuff like that. Now BCD is a binary coding form where this whole value 425 is not converted into its corresponding binary equivalent, but each of the digit is translated into 4-bit binary. So 425 in a BCD code, it will become binary 4-bit binary for 4, which is 0100, then 4-bit binary for 2, which is a 0010, and 4-bit binary for 5, which is 0101. So if you need to translate a 425 decimal into 4 with the 4-bit binary coded decimal way, then your answer is going to be like 12-bit, and it will be a sequence of 0100, 0010, 0101. Okay, so that's the BCD. Now here in this problem, what it is saying is that we need to implement a logic which will translate a 4-bit BCD. 4-bit BCD means it's a 4-bit input. First of all, it's a binary coded decimal. That means my value range is going to be 0 to 9, because that's what all the symbols of the decimal is, and where each of this decimal digit is converted into corresponding binary digits. So essentially we need to convert the decimal values 0 to 9 expressed in 4-bit, assumingly unsigned 4-bit, and convert into the XS3 code. So that's our specification for this specific problem. Now from this whole understanding of this requirement, what we can come up with a truth table formulation. First of all, it's a 4-input BCD. So let's call it an A, B, C, D, with A being the most significant bit and D being the least significant bit. And in a column, we are producing corresponding decimal digit values. So it's 0 to 9. And we write down corresponding binaries, right, in sequence. All the binaries till 9. Then on the output XS3 will be also 4-bit. First of all, 4-bit BCD into 4-bit binary, XS3. Let's call it an output WXYZ. WXYZ, okay, that's 4 input. My digital circuit has 4 input and that has 4 output. So this 4 output is WXYZ, and the binary correspondence of this thing is 0011, because why? Because your original BCD is 0, value 0, XS3 code would be +3, which is like 3 in binary is 0011. Similarly, 1 would be in the BCD would be 0001, and you add 3 on top of it, so its value is 4, it will become 0100. Similarly, we compute all the combinations of the outputs that need to be done. Like for example, 7 is 0111 in the BCD. You add 3 on top of it, the value becomes 10. 10 is 1010, right? So we make the truth table. Now in the truth table, if you recall, whatever we handled so far, we assumed we had number of inputs and one output, right? One function. Now here we need to have a 4 output. So they are fundamentally 4 different Boolean functions. So essentially we are encoding a function for W, function for X, function for Y, and function for Z. So if there is a 4 output from a digital circuit, you are essentially dealing with 4 truth table separately, and then optimize them separately, formulate them separately, and make them separately. Okay, so this is a fundamental concept. Now we have the truth table constructed, and from that we can definitely write down our formula in the SOP form, right? So for example, here the logic, your SOP form would be your sigma of m 5, 6, 7, 8, 9, right? Sigma of m, they're basically the mean terms are 5, 6, 7, 8, 9. And you would imagine, and someone can say, hey, what happened to rest of the bit combination? We have more, like 4 bit we can express till 15. What happened to 10, 11, 12, 13, 14, 15? So those things become don't care. Remember we discussed about the don't care term in Boolean algebra part 2 when we are discussing the K-map reduction. This is how the don't care term origin. By specification, it's by the specification it is implied that for the lifetime of this digital circuit, a binary combination at the input side belongs to 10, 11, 12, 13, 14, and 15 will never occur. That's by the specification. So that's why they become a don't care term for us. So in that way, we can define our sum of product standard form for the outputs, like this formulation. So from once we have this, then we pretty much know the steps, right? How to construct the K-map for 4 variables and optimize things. So we do that, right? This is what we do, and we use the X term, don't care term, in those K-map tables, and we concluded that your W function, optimized function, is this, X is this, Y and Z thus. So we write them down, right? And now what we need to do, like so far by manual effort, that we want to do some common logic between these 4 output functions, W, X, Y, Z. We can rearrange BC or BD as A or B and C or D. Similarly, we can do like B bar C or B bar D as B bar C or D, and then C bar D bar, we can make it a B, C or D whole bar. So that means look at between this W and X, C or D, we can reuse between these 2 output function. We can reuse them. This one becomes may become like C XOR X NOR D. CD or C bar D bar is practically your C X NOR D logic, and this one also, it becomes like an B XOR C or D, right? B XOR C or D. Now let's assume we don't have XOR gate in our library. We cannot implement with XOR gate, so we pretty much stick to our OR and 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 inverter gates. So here what we can do, once we understand this part, we draw the schematic circuit. So basically a schematic circuit would be like, okay, for W I need to use an OR gate between C and D, and that output need to be ANDed with B, and that AND output need to be ORed with A. So pretty much we are doing that. See here, C or D ANDed with ANDed with, this is C or D, this point is C or D. C or D is ANDed, oh here, ANDed with the B, ANDed with B, and that output is ORed with A, and that gives you the W function. X function is like we need to compute B bar, inversion of B, and C or D we and OR them together, so it becomes like your, this is your B bar and C or D, okay, and another is like C or D naught, which is C NOR ANDed with B, and then we OR it together, that becomes X. And our Z is very simple, it is D bar, simple one inverter get D bar, and your Y is C D plus C bar D bar, which is like C and D here, and C bar D bar, which is coming from, actually which is interesting, this is coming from here, which is basically C XNOR D, C XNOR D. Like what we did here, I should have one more steps transformation I should have shown you, which is C bar D bar is nothing but C or D whole bar, right, by De Morgan. So that's what we did here. C bar C or D whole bar, that becomes your C bar D bar by De Morgan, and we OR it with the other terms, and we get Y. C D, and we get Y on this. So this is where we stop at our class or our domain that we done with the logic circuit design. And oh, one more point, important point, is that we need to test it. So manually testing is that we provide different value combination here and follow through the logic manually, okay, write down each of this logic value for that primary input combination. By the way, we call this ABCD in the logic circuit sense as a primary input to the logic, and this WXYZ is the primary output of the logic. So we basically start putting different logic values, and for that, what it's this first stage logic translation, and then second stage and third stage. So basically we start putting logic values out of this output gate based on its input value, and ultimately comes down to WXYZ. Then we check it back with the truth table that whether it is matching the output sequence that for WXYZ is whether matching with that corresponding ABCD. So since this is a small circuit, right, and we have test pattern like need to be done from 0 to 9, 10 test pattern, so we are pretty much can do it manually, like it's a 10 testing, different testing, right? But this is not really for the practical circuits. Let's say a practical circuit has like, let's say even 8 primary input. That means your combinations of different unique bit pattern combination can be 2 to the power 8, right, 256. Okay, that's probably possible, like if you tediously do it manually. It depends also on the what circuit you are talking about. If it has lot of logic gates inside it, it's become impossible. Think a logic has like 20 primary input. It becomes 1 meg of combination, like 1024 multiplied by 1024. That many combinations you can have for a 20 primary input combinational circuit. There it is impossible, right? Completely impossible. So your any testing QA for the digital circuit works in that domain. How fast, how reliable can I test a circuit to find out any fault, any defect? Because it is not possible even for an automated computer program to test for that 1024 multiplied by 1024 different test pattern. That will take long time. Okay, so test and QA domain's main objective is that what is the minimal test I can make to qualify my digital circuit. That's very challenging area, and many computer science and electrical engineer together they actually work in that area for automated testing in a minimum time, that kind of problem. Okay, so that's all for this lecture 6. If you have any question, queries, please send me email or ask me in the class.